Hey everyone, this is Eddie Does Math. Welcome to my channel. Before I begin, if you want to check out the problems I'll be covering today with my personal annotations and solutions, just click the link below, enter your email, and you'll have it in your inbox in less than 30 seconds. Now let's take a look at some easy, medium, and hard level problems in Algebra 2. Let's start off with some easy level problems in Algebra 2. We have this polynomial, and given that x minus 1 is a factor of f of x, that's incredible information we're given here. Find the value of k. So using what we may call the factor theorem or the remainder theorem, we know that f of 1 is going to equal 0. Now, how do we know this? Well, x minus 1 is a factor of f of x. So if we plug in 1 into the x, we get 0 for this factor, multiplied by any of the other factors will give us 0 for the entire function. That's why we know that f of 1 will equal 0. So when we plug in 1 into each of these x values, I would get 1 cubed minus 3 times 1 squared plus k times 1 plus 8, and all this will equal 0. So we have 1 minus 3 plus k plus 8 is equal 0. So in the end, k will equal, I believe, negative 6. Because that will give us negative 2 plus 8 is positive 6 and negative 6. Great. So now we want to solve the equation f of x is equal to 0. So we know that x minus 1 is a factor, and we know now k is equal to negative 6. So f of x, if I were to work on letter b now, f of x is equal to x cubed minus 3x squared minus 6x plus 8. Now we know that x minus 1 is a factor, so let's, using inspection, go ahead and divide. X cubed divided by x is x squared. That leaves a negative x squared. We need minus 2x squared more, so I'm going to subtract the 2x. Then I get minus or positive 2x. Once we multiply the negative 2x times the negative 1, we need a minus 8 at the very end, and we recognize that negative 1 times negative 8 is that positive 8. If you didn't like this method, another way you could use is synthetic division. We could have done 1 minus 3, negative 6, and 8, and we'll divide by the opposite of this negative 1, which is that 1. So we bring the 1 down. 1 times 1 is 1. We add, that's negative 2. 1 times negative 2 is negative 2. And then once we have that, that'll be negative 8 once we add down. 1 times negative 8 is negative 8, and we get that 0. That's how we get 1x squared minus 2x minus 8. Great. Now this is also factorable. We need to set this equal to 0. So we have x minus 1 times x minus 4 times x plus 2 equal to 0. So my x values would be 1, 4, and negative 2. There we go. Question 2, another easy one. If b is a constant, what is the value of b such that p of x is divisible by x minus 2. This is another way of saying that x minus 2 is a factor of p of x. So that means p of 2 is going to equal 0. Very similar to the problem we just solved. So we're going to plug in 2 into all the x's that we see. So b times 2 cubed minus 6 times 2 plus 2b. Careful with the 6's and the b's. If we're writing too quickly, we may make a mistake there, so be careful with that. Now we have 8b minus 12 plus 2b is equal to 0. That gives me 10b is equal to positive 12. So b is equal to 12 over 10, which is 6 over 5. Let's solve some medium level problems now. Polynomials, graphing them can be difficult for many, right? Challenging to sketch these because it's very new, right? We're used to solving or sketching graphs of equations using transformations, but now this is a little bit different. So let's take a look. So from the graph, we know that the degree is 6. We observe the following. The graph touches and bounces at x equals negative 3. So x equals negative 3 is a root, but now we know that the multiplicity, the number of times this root occurs, is even because it bounces at the x-axis at x equals negative 3. Now the graph crosses the x-axis at x equals 1 and x equals 4. That means the multiplicity here will be odd. So what do we mean by this? P of x has roots negative 3, positive 1, and positive 4. Now the degree is 6. So let's say the multiplicity at x equals negative 3 is even. That means this has to be 2. But since the degree is 6, either one of these multiplicities, the powers here for x minus 1, x minus 4, needs to be greater than 1. Because if it were just 1 and 1, the degree of this graph, of this polynomial, will just be 4. But we need a degree of 6. So one of these 1s has to be a 3. That means there are many possible factored forms of p of x here. We could have x plus 3 squared, and then x minus 1 be the one that's cubed, and x minus 4 be the one that's to the first power. Another way we could write this is x plus 3 to the fourth power, because 4 is still even, and make the other ones a 1. So 1, 1, and 4 add up to 6, so that's another way to write it. Let me know down in the comments if you have any other ways we can write a factored form of p of x. These are the only 3 that I could find, but if you could find more, let me know. So now completing the square, also really difficult for students, not so much because it's challenging, but more so because we make many errors and we forget to add or subtract whatever we're implementing, whatever we're adding to the original to get this factored form. So I'll show you what I mean. The first thing we have to do is work with these first two terms. We got to divide by 2. So we get x squared by itself in order for us to be able to factor cleanly here. So this negative 7 becomes a negative 7 halves. Leave a little space, and we're going to add 2 at the end. We take half of b, half of the coefficient of x, and square it. So half of negative 7 halves is negative 7 fourths. We're going to square it. But keep in mind what we just did. We just added a value within the parentheses, and we've also multiplied that by 2. So what I have to do here is I have to subtract exactly what I just added inside to maintain the balance of this expression. Otherwise, we're changing the expression and it's no longer equal to what we started with. So now we can factor this out like this. 7 fourths squared is 49 over 16 times a 2 will be 49 over 8. And I can add that. 49 over 8. 2 is 16 over 8. So in total, we have this vertex form, 65 over 8, just like this. And completing the square is actually how we derive the quadratic formula as well. Now let's look at some hard level problems. Students tend to find imaginary numbers, complex numbers really challenging, and let's try to work with this here. Find the value of x and y, given that x and y are both real numbers. The first thing we want to do is we want to make this and bring it to the top, bring those imaginary numbers to the top so that we may be able to combine it with whatever we have on the right. In order to do so, I'm going to multiply 1 over 1 plus I times its conjugate. So 1 minus I, 1 minus I. This is also called complex conjugation. Once we do this, we'll get 1 minus I on top and 1 minus I squared. We're using the power of difference of squares here. So 1 minus I squared, reminder that I is equal to the square root of negative 1. So I squared is equal to negative 1. On the bottom here, we now have a 2. Since negative times a negative 1 is positive 1, 1 plus 1 is 2. So what we have now is 1 over x plus iy minus 1 minus I over 2 is equal to 2 minus 3i. If we added this to both sides, I would get 1 over x plus iy is now equal to 2 plus 1 half, which is 5 halves now, and negative 3i plus I over 2, which will be 7 over 2i. If I were to do this on the side here, basically 2 became 4 over 2, negative 3i became negative 6i over 2, and I added a 1 half and an I over 2. And that's how we got this right here. Ooh. And that's where I see the mistake. If I added an I over 2 to a negative 6i over 2, this should be a minus 5 over 2. Really glad I caught that mistake before I moved on here. And then 4 halves plus 1 half is indeed 5 halves. Okay, great. We're doing great here. That's why we always check our steps as we move along here. Awesome. So from here, we will try to find what x and y are. In order to do so, I'm going to go ahead and flip or switch this with this entire thing. And why is this possible, you may ask? Well, 8 over 4 is equal to 2, just like if we switch these, 8 over 2 is equal to 4. So that's why this is possible. So now we have 1 over, I'm going to put these together, by the way. 5 minus 5i all over 2 is equal to x plus iy. Now, if I do this, I get 2 over 5 minus 5i is equal to x plus iy. I need that I to be in the numerator. So what I'm going to do, I'm going to, again, use complex conjugation to bring that I to the top. So I'm going to work on this on the right side here. So I'll have 2 over 5 minus 5i, and I'll be multiplying by the conjugate. 5 plus 5i on both the top and bottom. So on the top, really easy, 2 distribute to both terms here. That becomes 10 plus 10i. And on the bottom, I'll have 25 minus the 25i squared. Now, I squared, again, is negative 1. So that means this becomes a positive 25. 25 plus 25 is 50. So I have 10 over 50 plus 10i over 50. So I found that x is equal to 1 over 5, and y is also equal to 1 over 5. Very neat problem here. Let's go over one more hard level problem. How can we solve the following in 2 different ways? Now, this one can get a little, intimidating, because we see 2 exponential terms being multiplied with 2 separate bases. And that's when we start to freak out a little bit. We're like, oh, how do we solve this? The bases aren't the same, and there's no way we can make this the same. This is when logarithms come in really, really handy. Let's take log base 2 of both sides. And using our logarithmic properties, I can split this, what is this called? This expression into 2 separate logs. So I have log base 2 of 2 to the x plus log base 2 of 3 to the x plus 1. Remember your logarithmic properties. If we're multiplying 2 things within the argument of a log, I can split it up as the sum of those 2 terms within those same logs with the same base. Now we can bring this x down and this power down as well. So now we have x, because log base 2 of 2 will just be equal to 1. This just becomes 1 since the base and the argument are the same, plus x plus 1 times log base 2 of 3, and that's equal to 5. Now, I'm going to go ahead and distribute x plus 1 or distribute log base 2 of 3 to the x and the 1. So I get x log base 2 of 3 plus log base 2 of 3. That's equal to 5. Now, I want all the x's just on one side, and I can factor right here. 1 plus log base 2 of 3 equal to 5. Bring this over to the right, minus log base 2 of 3, since these are all now constants. And I can divide both sides by 1 plus log base 2 of 3, just like this. Now, what's another way to solve for this? Well, let's check out 2 to the x times 3 to the x plus 1. We have 2 to the x times 3 to the x plus 1, and that's equal to 5. Well, 3 to the x plus 1 can be rewritten as 3 to the x times 3 to the first power, since when we using our exponential properties in reverse. Now, if we have the same, oops, I circled the wrong things. If we have the same power, if we have the same exponent here, then we can actually multiply the bases. So we have 6 to the x times 3 is equal to 5. So 6 to the x is equal to 5 over 3. And now we can take log base 6 of both sides. And this way might be the way that you prefer, actually. And so we bring the x out front. Log base 6 of 6 is 1. So x is simply equal to log base 6 of 5 over 3. Now, if you look at this and this, they will give you the exact same thing. And that's an awesome thing in mathematics.
If you found this video useful or you learned something new, make sure to like and subscribe. And if you want my personal annotations from this video, just click the link below, enter your email, and you'll have it in your inbox in no time. I teach these concepts and skills in my Algebra 2 course. We currently have a $7 7-day trial. I'll see you in my live lessons.